Okay. All right. Thank you again for listening to my talk. So what I'm going to be talking about here now is, again, sort of following up on what Paul said, this trend, going smaller and smaller. So one way is to basically do this integration on wafer scale level, and that's our ultimate goal. But interestingly enough, we're seeing a increased technology development in low-power systems for off-the-shelf components. So ultimately, this is all going to be made of this one type of system that we have on the wafer and the substrate, right? But right now we can actually see some interesting radios, low-power radios, low-power microprocessing units that are extremely low power, extremely small, all integrated, and we can actually get them off the shelf. And so basically, what we have seen happening is, we have this bigger systems that are progressively getting smaller and smaller, and now basically we're seeing electronics that contain both radio and actually quite impressive processing power, and still on average are able to use only single microwatts of power. Okay, now if we're at that power level, we can now start seeing systems. So no feedback. Maybe let's try to do something like this. Okay, we really start seeing systems that are being able to use all this energy that we can scavenge from the environment, right? So we're now starting to see systems that actually can use energy scavenging as a power source. And this is actually immensely exciting, and it's essentially two technologies coming together. We have been talking about it. UC Berkeley has essentially been the leader in energy harvesting field for a long time, and now we actually see this coming to fruition, where we get this low power systems that can actually use this. And so this has essentially been the enabling technology to do a lot of these things, because ultimately, when we have this system on a chip, we need to be able to power it somehow. And so now we can. And so so we see emergence of these systems on a chip from a number of suppliers. We worked with Texas Instruments and also Atmel has, without, I shouldn't endorse any players here, but really, it's all across the board. We see this very interesting systems, and so, really now we can start to basically use these systems to create this massively distributed sensing application we've been talking about, right? So either it's natural gas pipelines or electricity. We can now really start embedding these sensors in there, because we do have the hardware to be able to do that. So specifically for the two projects I mentioned before, we've used these nodes that you can get from Texas Instruments, and this is essentially how this node looks like. It's actually a development kit. So that's another interesting thing, is that these suppliers will actually provide you with enough hardware and software, so you can very easily start rapid prototyping the systems. And so actually we've been using that fairly well. It's pretty easy to set up a wireless network, low power wireless network. In this case, this plugs into a computer. This is a standalone system with a radio, a microcontroller, and then some input and output pins. You can connect it to your sensors, and you can start transferring data. This is essentially that same system. So right here, we can put it into and package it a little bit more, and now it becomes a node that we're going to put for the natural gas project, for example. We can put it on these pipelines, and they actually work very well. They're very reliable. So that's pretty exciting. But as we said, we're continuously looking for making it smaller and integrating it, because the smaller we can get it, usually it becomes less expensive, and usually it is easier to integrate. Okay. So this new system here that Paul mentioned briefly before as well, this is something that's quite new. It was actually also developed by initially a senior undergraduate student who actually stayed on to work with us a little bit. So very interesting piece of engineering. This whole system is contained within a half a cubic centimeter of volume. Okay, so it's actually the smallest radio sensor node that's built out of discrete components right now available. Okay, so it's a very tiny thing. You can see here, this is actually the printed circuit board on a penny. The amazing thing here is this is a 4-layer board. Okay, so actually 4 layers of interconnects here. Those are some of the components, the passive components, that enable the radio microcontroller, which is both a radio and a microcontroller, that's actually on the back side of this, and takes essentially the entire space of the circuit board to function. Okay, we can add a little antenna. We have some access ports here. We can actually program the device. We have some analog to digital I/O pins right here. And then if we stack this, if we add a battery onto it and some sensors, we have actually a completely self-contained unit. All right. So again, very exciting, very small, and now really non-intrusive. Right. We can really put it onto wherever we would like to make the measurements, and designed for low power. Okay. We can really, especially with this microcontroller, we can shut the entire thing off. Okay. Put it to sleep, like Paul mentioned, into sleep mode, where it actually uses less than a microwatt of power. Okay, it's barely alive. Okay, it's just sort of chugging along, and then it can wake up at a preset interval, do some sensing, go back to sleep. Okay, so designed for ultra low power. This is just another view of the top of the PCB, and you can see it's actually a very complex system. There's some programming ports, A to D converters, but it's essentially not only a sensing platform, but also a computational platform. Okay, so it's a microprocessor on a chip. Low power, again, low power. Of course, it is tricky to assemble these things. So designing it is one thing, but when you work with things at this scale, it is very difficult to be able to actually put these things together. Some of the components here are much less than a millimeter across. It's just it's hundreds of micrometers essentially. So assembling this thing, you actually have to use microscope and things like that. And so with discrete components, now we're really sort of this boundary between a system on a wafer, right, and a system on a sort of PCB board. It's kind of blurred, right? I mean, we're essentially already getting to microscale components even with these off-the-shelf units. So we're really pushing downwards on this thing. It's very exciting. Okay, this is actually a picture of that system. So this is the entire system here. Now the interface to program it, right, is actually bigger than the entire thing. So that's kind of exciting. Of course, that could go away, right? Once you program it, you can actually reuse it. It has non-volatile memory, right? Flash is a very interesting thing that enables a lot of these applications. So we can actually take those connectors out, and then we have all these modes. And of course, again, the programming and testing setup is a lot bigger than the entire device. These things work on building together a ad hoc network, right? So we've all heard about the Internet of Things. This is essentially what's happening here. So you can program this thing. It's, again, quite complex, computational-wise, to actually create this network, whereas, we have now many of these distributed nodes that are all everywhere, right? And they're now so small we can't really see them that easily, right? But they could be here low power, right? Extracting energy from the environment. Right? Now we can actually build up these networks and actually have a self-contained data gathering network that transmits the information. Right? If this is, for example, a technology that could be used to instrument the cables, like we talked about before. Right? So this network would actually be the network that maybe we would see in a manhole, right, inside a vault for a cable, locally collecting information, then putting it into a router or some kind of a device where that's being transmitted, say, back to the utilities. This is some of the data that we collected using this device. And so you can see here, this is essentially the voltage plot. It's actually quite tricky to operate this device in a sense that there's just so little power available in such a small footprint that we want to save every little bit of it. Right? So you can actually, wrong button. So you can actually see here, this is when we power up the device. There is a big drop. So the voltage here essentially corresponds to how much power is being drawn instantaneously. And we're looking at the voltage drop over the battery. Okay, that provides power to this device. And so the more power we draw, there is an internal resistance in the battery, and then we can actually draw. We can see the voltage drop over it. So it's essentially the power consumption. And you can see here initially there's a drop in the voltage, and then this chugs on, and then there is a measurement event, and you can see actually we send some information. We actually transmit a packet of information, go back to sleep, and recharge the battery. Okay, so all this has to be engineered such that if we fall below this line here, we're actually resetting the controller because we don't have enough power to keep its essential functions running. So a little bit tricky to engineer, but again, we can do this. You can actually see here there's some data that we got off the device. This was actually a current waveform. So we're actually sampling current, measuring current on a line, on an extension cord, and this is basically one cycle of that current measurement. And I don't remember actually right now what the current measurement was. We would need to calibrate this, of course, and there are some issues with that as well. But basically, in this case, we can actually measure current, and that's what this green node was designed to do. But as I said, it's quite complex, and so these things are basically built more and more of a sort of plug-and-play mode where actually these devices start to build up these networks, right, with almost minimum intervention, because there is so much layered hardware that's based on. And so if you write an application, even for that little tiny device, there are these different layers that we can access. There's the network layer, physical layer, hardware abstraction layer. So all of it, enables us to basically build some interesting self-organizing application, if you will, right? So you can build up these networks very easily to do the sensing. And then, of course, the suppliers, provide in all cases this development tool. So it's very easy. It's very sort of a rapid prototyping environment. We can very easily build up these networks and start playing, which makes it easier for us to do innovation, right? Because we can try things out much easier. And then this is just some testing. There are features like battery, like reading the battery voltage level on these devices. Of course, a must because we always have to have this in mind. The power limit, right? So when we design for this type of systems, we always have to be very mindful of the energy we have. And so there's going to be some other presentations further down this track where actually we're going to look at some energy harvesting and some battery applications, right? So it all sort of fits together. Now, this is really the hardware that can allow us to control some of these things such that we have these small, low-power, non-intrusive systems that actually collect the data we need to make all these applications possible. Okay, so I think that's all I'm actually going to say about these radios. Basically, what I want to convey to you is that we are really entering this domain where there are all these applications, all these platforms coming up that we can use off the shelf and enhance them, and even put them on a wafer further down the line that enable us now to do all these exciting applications, to harvest the energy for the sensing we need. So we can have sensors that are, we just put the sensor there and lasts, as long as the ambient energy is there, essentially, and transmits information. And we can really make these things really small and completely non-intrusive. Okay, so I think that concludes my portion of the slides. Thank you. Questions? Are there any questions about some of this at this point? Yes.
Yeah. So this is great, and I can see this kind of moving into the marketplace. So one of the inhibitors in this domain has always been network programs.
Mm-hmm.
And I'm just wondering if you see any emergence of a sense of urgency or cooperation in the marketplace that's going to allow this great hardware building or development capability to become deployed as network questions that are resolved.
Right. Well, so it's moving towards collaboration, I should say that. There are protocols that are being used for low-power wireless networks already. Things are built up that, it sort of started with the Zigbee protocol and sort of continued from there, although, the Zigbee is actually not a very good protocol to use. But there are protocols that are being used by widely for these type of mesh networks. Okay, there are updates that are coming. One thing that we noticed is, Arduino is a very popular platform. And so for microcontrollers, for building things. And so people are really wrapping things around that Arduino platform. And so, for example, for this application that I showed you here, there's at least one, but I believe there are at least 2 companies, actually, that are working on creating an Arduino abstraction layer to this device, right? So if you know how to program in Arduino, then you can program this thing, right, with a little bit more oomph to it, right? Because there are more different APIs that allows you to access all these, sleep modes and things like that. And so then you can very quickly actually program the device. So I think we're seeing this standardization across the board exactly for the reasons you mentioned, that there is, there's need for that, right? Because you're going to have this network of many devices by many suppliers that need to talk together, right? No. Yes.
Actually, sort of drilling one level down on that in terms of the sysadmin challenges of large networks like this. Identifying some of the components might be one of the things. You have to keep track of the devices with either their physical geographic location or the port name, the motor.
That's right.
They're on. You need to timestamp the data. There's the issue of calibration
Yep.
and then correction. These are trade-offs. So
Right.
calibration, maybe that's distributed. There's known good propagates.
Right.
Issues like that. And some of this shows up as a sysadmin burden, and some of it shows up as an opportunity
Right.
for building robust systems. Do you have any thoughts at this? The administrative challenge that these large networks, potentially large networks, will bring to us.
Right. So the short answer is yes. Right. I think those are very challenging problems, and there's a great deal of opportunity. Right. So the question is, do I want a whole lot of bad data or inaccurate data, or do I need just a little bit good data? Or, how do I do this? How, what happens if there's a new node on the network? Security is an issue that actually you didn't mention, but that's a huge issue, right? What if I have a bad node on the network, right, that is maliciously polluting the information that's being sent across, right? And how do you deal with that? So there's many issues. There's lots of research going into it. But I think the exciting part from my perspective really is that now we start to see the hardware that we can actually experiment with and look at these issues. Because a lot of research up now is sort of theoretical, but now we're starting to get the hardware that actually we can now try it out. And as soon as you have the hardware, there will be issues that will come up that you didn't expect, and some of the issues that you did expect will not come up. So I think that's the exciting part. But yeah, there's lots of research potential and challenges. Yeah. Okay. Thank you.